Cephalosporins are a highly potent class of beta-lactam antibiotics. Originally isolated from Cephalosporium fungi, these molecules aggressively target and dismantle bacterial defenses. To understand the mechanism, observe penicillin's baseline architecture, a square beta-lactam ring fused to a 5-membered biozolidine ring. Cephalosporins diverge. Their beta-lactam ring fuses to a 6-membered dihydrothiazine ring. This atomic expansion creates chiral carbons at C6 and C7, rigid pivot points governing 3D shape. This specific atomic arrangement enables a highly precise system of modifications known as the structure-activity relationship. By substituting individual atoms across 8 key positions, researchers can modify how the molecule behaves in the human body, its breadth of bacterial targeting, and its ability to resist enzymatic attacks. The cephalosporin scaffold acts as a highly customizable modular platform, engineered atom by atom for precise antimicrobial combat. Before making chemical modifications, we must establish the biological target. All beta-lactams hunt penicillin-binding proteins, or PBPs, located on the bacterial cell membrane. The square beta-lactam ring acts as an irreversible inhibitor of one highly specific PBP, an enzyme known as transpeptidase. Transpeptidase performs a vital mechanical function. It cross-links NAM and NAG peptide chains, knitting them together to form the bacterial cell wall's structural mesh. When the beta-lactam ring binds to transpeptidase, that NAM-NAG cross-linking process abruptly halts. The structural integrity of the wall degrades instantly. Without a stable perimeter, the compromised cell wall can no longer contain the dense internal pressure of the bacteria. Hyperosmolarity forces extracellular fluid rushing into the cell, causing the bacteria to swell uncontrollably. By stopping transpeptidation, the antibiotic turns a routine bacterial metabolic process into a guaranteed catastrophic cellular rupture. This 3D molecular model allows us to map exactly how structural edits modify that destructive capability. We start at position 1, the sulfur atom on the dihydrothiazine ring. If you oxidize this sulfur atom, converting it into a sulfone or sulfoxide, the resulting chemical shift actively decreases the drug's antimicrobial activity. However, if you strip the sulfur out entirely and replace it with a single oxygen atom, the modification enhances overall activity. Alternatively, attaching a methyl group directly to the baseline sulfur atom does not impact receptor binding, but it significantly increases the sheer physical stability of the ring itself. Moving down the ring structure, we hit position 3, marked here by a generic X placeholder. Swapping this X out for a CH3Cl group structurally converts the molecule into an orally active compound, allowing it to survive the digestive tract. If you substitute a 5-membered heterocyclic ring at position 3 instead, the edit drives a much higher baseline of antimicrobial activity. Bridging carbon 3 and carbon 4 is a strict double bond. This state of unsaturation is biologically critical. Reducing it to a single saturated bond immediately terminates all drug activity. Finally, to maintain basic functionality, the atoms at positions 2, 5, 6, and 8 must remain completely untouched. The dihydrothiazine ring is effectively a thermodynamic chassis. Precise atom swapping here dials in the molecule's physical durability and delivery method long before it ever encounters a bacterium. Look at position 4 on the model. A native carboxylic acid group here is strictly essential for baseline receptor binding. If you replace this vital carboxylic acid with an ester group, you intentionally inactivate the drug. This creates a prodrug. The esterification massively increases the compound's bioavailability, allowing the inactive, highly stable molecule to safely absorb through the gut and into the bloodstream. Once administered, native liver enzymes cleave the ester bond. This restores the carboxylic acid and reignites the drug's antimicrobial activity in vivo. Shifting our focus to the top of the molecule, we reach the R group attached to position 7. Specific acylation at this C7 position chemically biases the molecule, tuning it to aggressively target gram-positive bacteria. Substituting this R group with a dense hexagonal phenyl ring broadly amplifies the molecule's overall efficacy across multiple bacterial strains. Positions 1 and 3 build the vehicle. Positions 4 and 7 dictate exactly how the drug survives human physiology and which specific bacterial armor it is equipped to pierce. This clinical matrix charts the 4 generations of cephalosporins, plotting their efficacy against gram-positive and gram-negative organisms over time. First-generation drugs, developed in the 1960s, are anchored by the prototype drug cefazolin. Cefazolin executes with high efficacy against gram-positive organisms, like streptococci, but it exhibits an inherent weakness against gram-negative bacteria. Gram-negative bacteria adapt by deploying beta-lactamase, an enzyme that hydrolyzes the C7 amide bond and completely neutralizes early beta-lactams. Second-generation drugs, like cefuroxime, were structurally tweaked to resist these gram-negative beta-lactamases. This shifted their primary effectiveness strictly toward the gram-negative spectrum. The leap to the third and fourth generations, with drugs like cefixime, achieved a true, robust broad-spectrum profile. Late-generation cephalosporins achieved a critical pharmacokinetic milestone, the physical ability to penetrate the blood-brain barrier and enter the cerebrospinal fluid to treat severe neurological infections. The clinical generations represent a decades-long chemical arms race. Pharmacologists repeatedly sacrificed absolute gram-positive potency in exchange for broad enzymatic invulnerability and deep tissue penetration. All of this raises a structural question. Is the secondary 6-membered dihydrothiazine ring strictly necessary to inhibit transpeptidase? The answer lies in a distinct subclass of beta-lactam antibiotics known as monobactams. Look at this structural comparison. Unlike the fused cephalosporin core, the monobactam drug aztreonam utilizes a beta-lactam ring that stands completely alone. It is totally unfused to any secondary ring. This isolated structure dictates extreme clinical specificity. Monobactams abandon broad-spectrum capabilities entirely. Instead, this stripped-down molecule exclusively and surgically targets aerobic gram-negative bacteria, like Pseudomonas. Separating the beta-lactam ring proves that transpeptidase inhibition is an intrinsic property of the 4-membered square ring itself. The secondary fused rings merely act as delivery and targeting vehicles. Cephalosporins function as highly modular chemical platforms. Altering positions 3, 4, and 7 directly controls human absorption, bacterial targeting, and enzymatic evasion. We can utilize a complex fused 6-membered system to penetrate cerebrospinal fluid and fight meningitis, or strip the molecule down to a solitary ring to snipe aerobic gram-negatives. Regardless of the generation or the exact structure, the biological endgame remains identical: the catastrophic halting of cell wall synthesis. Mapping the structure-activity relationship of cephalosporins proves that the future of antimicrobial therapy relies entirely on the precise, rational engineering of atomic geometry.